Our next major topic is going to be nervous tissue. And the way I like to teach nervous tissue is through a metaphor. And I call the metaphor the umbrella metaphor. The reason I call it the umbrella metaphor is because whether you're aware of it or not, each time you hear rain, your brain has to make the decision of whether you take an umbrella or not. And what I really want to get at is that's what neurons do, is they make decisions. But before we get into that in too much detail, I just wanted to give you the heads up of what the expectations are for this test. And basically the expectations are that you're going to be able to reproduce this whole drawing. Now this is a simpler drawing right now. I'm going to take you up through 3 layers. By the time we get to the 3rd layer, it's going to be a pretty complex drawing. The main philosophy here is that if you can put everything into a story, then you really kind of understand everything. If you look individually, I've got things kind of like chapters in a book. There's a question 1, a question 2, a question 3. And my hope is that each individual question, I can explain it well enough that you understand that little piece of the puzzle. But then it's going to kind of be on your shoulders to put those pieces of the puzzle together to see the big picture. And if you do make it through that step to seeing the big picture, then you basically understand everything about how neurons make decisions. It's going to be really hard for you to just memorize this without understanding things, and that's kind of the overall point. Now if you think about it really briefly, you can understand how you make decisions. There's usually pros and cons. Those pros and cons might be of different strengths. But what we're trying to get down to is how the neuron makes that decision for you. The other reason we're doing this today is basically this is our first step in understanding how some of the major electrolytes play a huge role in overall health. So we're going to talk a lot about sodium and potassium, calcium, and chloride today. Those are going to be flying around all over this sheet of paper. And so those are major electrolytes that we talked about when we talked about chemistry, and I told you you needed to have a basic understanding of ions and things like that. And those are going to play a critical role in how neurons make decisions. And these ions are going to just keep popping up. They're going to play a role in muscle contraction. They're going to play a role in how fast the heart beats, how hard the heart beats. They're going to play huge roles in how the kidney filters. And so this is kind of our first step in really understanding that if sodium and potassium get off, a lot of things can go wrong in the body. Sodium and potassium hardly ever get off in the body, and the body is just so good at controlling their concentrations, usually through the kidneys. But if they do get off, it's really, really tragic. And examples that you might be able to think about are Terry Schiavo. She had a problem with potassium levels. Basically, it was tied to diet. Then also the water drinking contest would have diluted out all these ions. Would have disrupted neuron function, so the woman became demented. It also would have caused edema, would have caused brain swelling. Where we're going to start on this umbrella metaphor is down here, number 1. I don't know why exactly I put everything in this kind of order. I think mainly when I first started to draw this out, this cell model here at the bottom is going to be least important by the time we get to the end. So I think that's where we have to start, but it's at the bottom because it's the least important later on. So again, this circle here is basically a cell model. It can represent any cell in the whole entire body. It certainly represents this neuron here, maybe just the soma or the cell body of this neuron. But it's just a cell model, a model of any cell. And the first thing I want to go into is something called the sodium-potassium ATPase, because it sets up some initial conditions that are common in all cells. So what the sodium-potassium ATPase does, just by the word ATPase, means it's an enzyme that breaks down ATP. And when it does that, it moves sodium and potassium. So sometimes it's called the sodium-potassium pump as well. What it specifically does, and I've just got one drawn here, but there's going to be millions in the cell, is it pumps 3 sodiums outside the cell, and in exchange it puts 2 potassiums back in the cell, and it burns an ATP. So it pushes 3 sodiums out, 2 potassiums in, and burns an ATP. There's going to be 2 results of that. I think the first one is pretty clear, that it's going to push all the sodium to the outside of the cell. So you notice I got a lot of sodium on the outside of the cell, and it's going to pump potassium inside the cell. So it's going to set up this chemical gradient, where sodium's on the outside and potassium's on the inside. Maybe a little bit more difficult to see, but if you pump 3 positive sodiums out and only 2 positive potassiums back in, you're essentially putting positive charge on the outside. Now the first guy that ever talked about this, he could have talked about this in 2 ways. He could have said the outside of the cell is positive relative to the inside, Or he could have said the inside of the cell is negative relative to the outside. Now either one of those is true, and he just chose to talk about the inside of the cell relative to the outside. So we speak of the inside of the cell being negative in charge. We express charge in volts, and so in our case it's right around minus 70 millivolts. Just to make it a little bit more confusing, this is called voltage of the membrane. So Vm equals minus 70 MV. I just wanted to add too, just at the end here, that this setting up this gradient again is common in all cells. In neurons, we've kind of set up a battery here though, so we've got charge on the inside, and we can change that voltage. We can let this go up to positive voltages. Essentially, that's an electrical current that neurons can use to carry electricity and make decisions really, really quickly. But again, all cells set up this gradient, and we kind of talked about this when we talked about active transport, that if you put all the sodium on the outside of the cell, it kind of acts as an exchange or a bartering mechanism where you can let the sodium come back in if it's going to bring something else like glucose back in with it. Our next chapter or question is, why do ions move? And it's fairly simple, but just wanted to point out really basically that if you allow sodium to move, maybe you make a channel or a hole in this cell so that sodium can move, where and why is it going to move? I think the first one's fairly obvious, that sodium is going to want to move in just by diffusion. Diffusion means that things don't like to be next to each other, like things don't like to be next to each other. So if sodium can, it wants to move inside the cell because there's not as much sodium there. So the sodium-potassium ATPase is going to set up a gradient, where sodium is going to move in because it wants to get away from other sodiums, and potassium wants to move out because it wants to get away from other potassiums. So they're going to spread by diffusion. Again, a little bit less easy to see is there's also an electrical gradient, where sodium is a positively charged ion. It would sure like to get inside the cell where the inside of the cell is negative. So just based on charge attraction, the positive wants to be next to negative. So sodium wants to move in by electrical gradient. Potassium has just the opposite desire. So potassium likes to stay inside of the cell because it's a positive charge and it's next to the negative charge. And so it's happy where it is. So then the question becomes, what happens if you open up a hole or open up a channel so that potassium can leave? It's going to leave because the chemical gradient is more powerful than the electrical gradient. So if you opened up a channel and let potassium do whatever it wanted to, it's going to want to leave by the chemical gradient. The electrical gradient is going to hold it back a little bit, but the chemical gradient is going to win. Another little detail to point out too is if you could open up a channel that would let both sodium and potassium flow through it, sodium is going to flow in faster than potassium is going to leave. And the reason is because both the chemical gradient and the electrical gradient are making sodium want to come in. The chemical gradient is wanting potassium to leave, but the electrical gradient is wanting it to stay. So in the case of potassium, one force is pushing out, one force is drawing it back in. And that's going to come up in like the muscle. In muscle, when you open up an ion channel, it's an ion channel that will let sodium and potassium both flow through it. That doesn't happen very often. Most of the time, an ion channel is just going to let one type of ion flow through it. So there's a sodium ion channel, a potassium ion channel, but only rarely will the channel be a sodium and potassium ion channel. But again, in this particular sodium and potassium ion channel that's in muscle, sodium is going to come in faster than potassium will leave. Our next question up here, question 3, is how do ions move? So we've just established in question 2 that ions will move if they're allowed to. So then how would they be allowed to? And the answer is ion channels. There's 4 basic types of ion channels, and really the only 2 that we're really worried about at this point are voltage-gated and ligand-gated. But we're going to bring in mechanogated and leak-gated just so we can talk about all the different ion channels, and also mechanogated and leak channels will come up when we talk about senses. So let's begin here at the voltage-gated channel. The first thing I want to point out is a gate. So this right here is a gate that's going to keep the channel closed. And I got it kind of hard to see. It's hard to see, but it's kind of an L-shaped gate. Another thing to point out are that there's these little positive charges along the gate. Now if the inside of the cell, like we said before, is minus 70 millivolts, these positive charges on the gates are attracted to that minus 70 inside the cell. So this gate is going to slide in this direction, and that's the closed position. Now what if that voltage changed from minus 70 up to something like plus 30? Now I want to be clear at this point that it doesn't necessarily always have to jump up to plus 30. Sometimes it just jumps up to minus 55, just a small change in voltage. But I'm doing plus 30 just because it's more extreme. It's a little bit more helpful to demonstrate how this gate is going to open. But if it's plus 30, then these positive charges say I'm not really attracted to the inside of the cell anymore, and so the gate slides out. And that is what opens the channel. So the pluses are attracted to the minus 70, gate slides down and stays closed. Pluses are not attracted to the inside of the cell because now it's plus 30, the gate slides open. A little bit more simple is a ligand-gated channel. Basically a ligand-gated channel also has a gate that I'm showing right here. And what it does is it can bind a chemical. Here I've got a little chemical, maybe it's a neurotransmitter, that binds to that gate and opens up the gate so that sodium can flow in. If there's no chemical bound, like in the case over here, then the gate tips shut and sodium can't enter. Just quickly, because again we won't really talk about these here, we'll talk about them later, are mechanogated. Mechanogated, there's a similar gate like the voltage-gated channel, and it responds to force. The main example is going to be in the inner ear, and it will respond to the force of a sound wave. So a sound wave will push on this gate and open it up, or if there's no push, then the gate will close. There's also what are called leak channels, which I've tried to draw smaller here, and these are always open. Small little sodium channels that are always going to let sodium flow in, small little potassium channels that are always going to let potassium flow out. And again, these won't really come up until we get to special senses. The next little chapter is relatively easy, I hope. And I just want to point out what happens when ions do move. So if we go back down here to our model cell, just pointing out the sodium wants to move in. What's going to happen to this minus 70 millivolts if sodium is allowed to move in? Well, now you've got positive charge entering the cell, so that's going to make this minus 70 more positive. So when sodium is allowed to come into the cell, this voltage is going to change towards the positive. Depending on the type of cell, it might swing all the way up to positive 30. Now what would happen if we opened up a channel and let potassium leave? Remember, if you open up a channel, potassium will leave, and it's going to take its positive charge with it. When it takes that positive charge, it's again like pumping that positive outside the cell, which makes the inside of the cell more negative. So what you have here is a way to change this voltage back and forth, up to positive voltages and back down to negative voltages. If you open up a channel and let sodium come in, we go up to positive voltages. If you open up a potassium channel and let it leave, we go back down to negative voltages. So we can switch this back and forth. The only other thing I wanted to point out in this first version is what I have over here are the basis for making this decision. So again, neurons make decisions, and those decisions will have pros and cons, so positive and negatives, and those pros and cons can have various strengths. So our umbrella, our metaphor here is the umbrella metaphor because it's do I take an umbrella today? When I was developing this metaphor, it reminded me of my daughter who really, when she was around 2 years old, really hated the rain. And obviously I learned that the hard way because the first time I took her out, I was like, let's just be tough and we'll just go without an umbrella. We'll run and we'll be quick. Suffice it to say, this was one trial learning. It was the last time I ever did that again because it was not a good situation. So from then on, I knew that if I had Ella with me, I was going to take an umbrella. And you can look around this neuron, and you can look at different things that might weigh in on whether you take an umbrella. I mean, most of the time, most people are like, I'm tough. I don't need to take an umbrella. That's going to be a con. I already have too much to carry, so I'm not going to take an umbrella. Maybe the only umbrella you can find is your Crayola or your Hello Kitty umbrella, and I'm not going to carry a Hello Kitty umbrella. I'd rather get soaking wet. Now, there's probably reasons why everyone would take an umbrella. Maybe if you're at a wedding. Maybe if you're at a funeral, not to be a downer, but that's the main example. That's probably the only time I'll use an umbrella these days. Maybe your mother-in-law tells you it's going to rain, and so That's going to be a really kind of a weak pro. Maybe you know it's the beginning of the semester, and if you're arriving a little bit late, the parking lot is going to be hugely full, and so you might take an umbrella then, knowing that you might have to walk a long ways. Or another example there, maybe you live in Iowa City, and there's just no parking in Iowa City, or at least when I was a student there was no parking, so you had to walk all the way to class. And so then I maybe took an umbrella. Or maybe your hair's just looking really fine today, and you're like, I got to take an umbrella today. So anyway, the main point here is that neurons have to put all these things together. Am I going to a wedding? Am I parking? And whether you're conscious of it or not, these kind of little factors are factoring into whether you take an umbrella as soon as you hear those rain droplets on your roof. Now, I don't want you to think that there's one neuron that's making this decision for you. It might be a group of neurons. Nobody really knows how this works. But at some level, there is a single neuron or a group of neurons putting together all these pros and cons to make the decision of whether you take an umbrella or not. Alright, so that's it for the first version. We'll head into the second version now. Okay, so this is a second run-through of 3 run-throughs. And I'm going to try and make sure that each one of these run-throughs stand on their own. So I'm going to cover everything again that I covered in the first run-through. I'll probably be a little quicker on this second run-through, but it's good to hear things a second time. So again, we're doing an umbrella metaphor here. Basically, the main point is that neurons make decisions. And we all know that decisions involve pros and cons. And those pros and cons can be of various strengths. So what we want to know then is, how does the neuron apply pros and cons? And how do those pros and cons have different strengths so that the neurons can make our decisions for us? And where it all begins is in the model cell. And again, this is a model cell. It could be any cell in the whole entire body. It's a little bit more specific to neurons now because I'm adding voltage-gated ion channels to it. But essentially, all cells in the body are going to have something called a sodium-potassium ATPase. And that's going to set up some initial conditions in every cell. But these initial conditions are really important in neurons to allow them to use electrical signaling, which is really, really quick. So first of all, the sodium-potassium ATPase, or sodium-potassium pump, pumps 3 sodiums outside the cell for every 2 potassium it pumps inside the cell, and it burns an ATP. This creates 2 gradients. The first gradient is chemical, which simply means that if you pump sodium out, sodium's going to end up on the outside. And if you pump potassium in, potassium's going to end up on the inside, and that's a chemical gradient with sodium on the outside and potassium on the inside. A little bit more difficult to see, not a whole lot more difficult, but a little bit more difficult to see is that if you pump 3 sodium out, you're pumping 3 positive charges out. And if you're only pumping 2 potassium in, then you're pumping 2 positives in. So you're essentially pumping positive charges outside the cell. That's going to result in more positive charges being on the outside of the cell than inside. And the first guy basically got to decide if he wanted to say, is the outside of the cell positive relative to the inside, or is the inside negative relative to the outside? And he chose to talk about the inside of the cell. So we talk about how the inside of the cell is negative relative to the outside. And we express that charge in voltage. And it comes out to about minus 70 millivolts. This charge is called the voltage of the membrane, or VM, and VM is equal to minus 70 millivolts. So now we've set up these gradients where sodium is stacked up on the outside and potassium is stacked up on the inside. It's pretty obvious that these ions are not happy this way. They'd like to move. But there's actually 2 reasons why these ions would like to move. The first one is, like I said, just diffusion. Sodium would like to get away from other sodiums, so if it could go inside the cell, diffuse inside of the cell, that would make it happy, so to speak. If there was a channel that opened up and let potassium flow through it, then potassium's going to diffuse out just so the potassium can get away from other potassiums. And those are chemical gradients. There's also an electrical gradient, and that's set up by this minus 70 millivolts. Sodium is a positively charged ion. It's attracted to negative charge. And so it would be attracted to the inside of the cell and would like to come inside the cell. Potassium is positive, and it's kind of happy to be up next to this negative charge. And so it's following its electrical gradient already, and it would like to stay. What that means is sodium wants to come in for 2 reasons, the chemical gradient and the electrical gradient. Potassium wants to leave because of the chemical gradient, but it wants to stay because of the electrical gradient. But the chemical gradient is much more powerful. Therefore, potassium will leave if an ion channel opens. And the other more specific example that I mentioned in the first run-through is tied to certain sodium and potassium ion channels. That doesn't happen that often. Most of the time it's just a sodium ion channel or just a potassium ion channel. But if you had a sodium and potassium ion channel, which you do in muscle, then the sodium is going to enter much faster than the potassium is going to leave. The third thing we talked about is we're talking about how these ions want to move. Well, how would they move? And the answer was ion channels. There's four main types. There's voltage-gated, ligand-gated, mechanogated, and leak-gated. And we're really only concerned with voltage-gated and ligand-gated at this point. You're going to see these pop up throughout this. We see some voltage-gated channels here, some voltage-gated channels here, and later you'll see some ligand-gated channels. Mechanogated and leak channels come up later when we talk about special senses. But let's talk again about the mechanisms of these voltage-gated channels. Essentially, there's a gate in this voltage-gated channel, and that gate has positive charges on it. Those positive charges are attracted to the inside of the cell when the inside of the cell is minus 70 millivolts, and so it slides down and it keeps the channel closed. If for some reason the voltage would change up towards the positive, and again I wrote plus 30, but it could be as little as minus 55, well now that positive charge is not as attracted to the inside of the cell. The gate slides out a little bit and the channel is open so sodium can come in. That's how voltage-dependent channels open. Ligand-gated channels, another name for ligand is chemical, and it's usually a neurotransmitter in our case. If that chemical binds to the gates, it's going to open it and allow ions to flow. If there's no ligand, no chemical, then the gate won't remain open or won't open, and it's going to remain closed. Mechanogated or mechanosensitive channels basically have the same kind of gate as a voltage-gated channel. It might actually be kind of a hair that sticks up out of the channel, and when force pushes on that hair, it opens up the channel. When there's no force, the channel stays closed. And usually, the main example of this is going to be sound-sensitive channels in the inner ear. When a sound wave hits the ion channel or hits the gate of the ion channel, it opens. If there is no sound and no force, then the channel stays closed. The last one is leak channels. Leak channels are really small channels that just remain open all the time. They might let sodium come into the cell, or they might let potassium go out of the cell. The next thing we're going to start to talk about are what are called action potentials. And before we get to that, I want to go back to the cell model and get a little bit more specific about the types of voltage channels. I guess I should have done number 4 up here first, which is just to point out that when sodium comes into a cell, it's bringing in positive charge. And that's going to make the inside of the cell more positive. If we opened up a channel to let potassium out, then that's going to make the cell more negative because a positive charge is leaving. So now let's get more specific about these voltage-gated channels. I want to start with the voltage-dependent sodium channel. First of all, it opens at minus 55 millivolts, so you only need a small change in voltage from minus 70 up to minus 55 to open this channel. The other thing about the sodium-dependent or the voltage-dependent sodium channel is it has an inactivation plug, a little plug that will swing in and close the channel. It's just got a small little timer on it that once the channel has been open for a while, it swings in and closes the channel. Voltage-dependent potassium channels don't have that plug, and they open at a different voltage. They open at plus 30 millivolts. So already, hopefully you're starting to see that there's a potential for a sequence here to change the voltage. If signaling, like we talked about before, involves changing this minus 70 up to plus 30 and then back down, we kind of have all the pieces to do that. If something causes us to get to minus 55, the sodium channel opens and sodium starts pouring into the cell. That sodium that's pouring into the cell is going to make the voltage go even more positive. And it's going to make it keep going positive until we get up to plus 30 millivolts. And when we get up to plus 30 millivolts, the potassium channel is going to open. The plug is going to go into the sodium channel, so it closes. Potassium is going to flow out and bring our voltage back down negative. Now we can formalize these voltage changes in a graph like this, where we have the voltage of the membrane here, and those key voltages we've been talking about, minus 70, minus 55, plus 30, are all here on the y-axis. What we have here on the x-axis is time. And so we're going to track that when you're sitting there and it's not raining, your umbrella neuron is sitting in what's called the rest state. It's not doing anything. There's no reason for it to do anything because there's no rain. As soon as there's drops of rain on the roof, something is going to get us up to minus 55 millivolts. And we're going to talk about that something in a second. But something's going to get us up to minus 55 millivolts. When we get up to minus 55 millivolts, this voltage-dependent sodium channel is going to open and start letting sodium come in. So sodium is going to enter the cell, and like we said, when sodium comes in, it makes our voltage more positive, so our voltage starts to go up. This is called depolarization. When we get up to plus 30, so now we're at plus 30, the plug is going to come into the sodium channel, and the potassium channel is going to open. So potassium is going to leave the cell and take our voltage more negative. And there's a little bit of an undershoot or an after hyperpolarization, or it's just called a hyperpolarization, when the potassium channel stays open for just a little bit too long. And our voltage goes down from minus 70 to like minus 80. We recover through the sodium-potassium ATPase. It puts all the sodium back where it needs to be, all the potassium where it needs to be, and we get back to minus 70 millivolts, and we sit in rest mode again. Now there's a couple of things else to point out about this. There's something called refractory periods. There's an absolute refractory period and a relative refractory period. What an absolute refractory period means is you cannot get another action potential once you've already started an action potential. So there's no super duper action potential, there's no big action potentials. Action potentials are always the same size. And the reason they're always the same size is because once you've opened those sodium channels, they all open. There's no like opening a few more. There's none that lay and wait to see if you got a super duper signal. They're all open. So there's no such thing as raising the voltage past plus 30. You're already raising it as far as you can. So that's an absolute refractory period. You're in the middle of an action potential. You can't have another action potential in the middle of an action potential. There is something called a relative refractory period, and that begins after the voltage starts repolarizing. This phase is called repolarization. And the idea here is that after all the sodium channels have closed and the potassium channels are open, you can reverse things. You can get the action potential to go back up. But it's really, really hard to do. And the reason it's hard to do is if you think about it, all those potassium channels are opening. So potassium is leaving, making your voltage more negative. So even if you open up the sodium channels, it's kind of like trying to fill the bathtub up with the drain open. So sodium's coming in, making you more positive. Potassium's leaving, making you more negative. So a whole lot more sodium has to come in than potassium is leaving. And that can happen to reverse this, but it doesn't happen very often. So basically, if you want to reverse and get another signal right away after a first one, it's got to be a really, really, really strong signal. So those are action potentials and refractory periods. The next thing I want to come to is down over here. And I want to talk about this again, just the neuron model, because I want to talk about how what we're talking about here is a neuron that's trying to make a decision about, do I take an umbrella today? And I want to be clear that this is a metaphor. There may not be just one particular neuron that makes that decision. It might be a clump of neurons, it might be a whole bunch of neurons. But in the end, neurons make yes and no decisions. Do I take an umbrella? No, I don't take an umbrella. Do I turn my car a little bit to the left so I stay away from the side of the road? Do I turn it a little bit to the right so I stay away from the center of the road? Is that a T or is that an I? Is that the word the or is that the word them? These are all small little decisions that neurons have to make for you, and all of them involve pros and cons of various strengths. And so what I have here is just my umbrella neuron, a drawing of my umbrella neuron, which is, I mentioned already that Ella, when she was 2, she hated the rain, and this was one trial learning. I took her out one time in the rain without an umbrella, and I never did it again. So she's a very strong pro in influencing whether I take an umbrella. Maybe parking is a positive, maybe a wedding is a pretty strong thing, and then maybe my mother-in-law is kind of a weak pro, because maybe my mother-in-law says, DJ, it's supposed to rain, you better take your umbrella. Now I'm going to listen to that, but I'm probably not going to run over and grab my umbrella right away. But also, just as something looking forward, you have to keep in mind that maybe this thing can become a stronger pro. Maybe my mother-in-law has a really uncanny ability to know when it's going to hail or something like that. And she will say, well, it's going to rain today and it's going to hail. So this pro has to be able to learn to get stronger. There's also negatives or cons, like maybe the only umbrella I have is a Hello Kitty. That's true. I've never bought myself a nice male-like umbrella because I've always I'm just going to be tough. I'm going to run, I'm going to get wet, it doesn't really matter, or I have too much to carry. So you get this idea that there's pros and cons, and there are various strengths. Now for the first part here, we're just going to talk about the pros and the various strengths. How do you get the various strengths? And it comes down to something called Ohm's law. Ohm's law is basically used mainly in electricity, and what it usually describes is electricity will flow faster if there's more of a driving force behind it and less of a resistance. But this relates to almost anything that flows, whether we're talking about water through a hose or sodium trying to get to sodium channels in what's called the axon hillock. It's all going to be determined by how fast that sodium flows. It's going to be determined by how much it wants to flow, what's the driving force behind it, and how much resistance is there. In order to describe this maybe a little bit more simply, I'm just going to say that there's something down here called the axon hillock, and there's a whole bunch of voltage-dependent sodium channels here, and they're waiting to get to minus 55. So if you're going to kick off something called an action potential, you've got to get these sodium channels activated. You've got to get them to minus 55. Now before I progress here, I want to take a step away and describe something called an action potential versus a graded potential. I've got a little cartoon down here just to show you what a graded potential is. In a graded potential, if sodium just comes into a channel and spreads around, that's a graded potential. So it's like sodium coming in and spreading around. And that's different than an action potential, where if you have a bunch of voltage-dependent sodium channels or voltage-dependent ion channels, when sodium comes in one, it's going to move to the next one and change the voltage of that one, cause that channel to open, and now more sodium is going to come in. And now the sodium is going to make this voltage change around this channel, so it's going to open and more sodium is going to come in. And you can see that it's kind of a stepwise change. So maybe it's the difference between one person throwing a bucket of water on a fire versus a chain gang, where you're basically passing a bucket of water repeatedly to put out a fire. These graded potentials occur out here, so these things are going to let sodium into a cell, but they're just going to basically spread out. They're not going to get any help propagating. But action potentials occur here. And just like I had voltage-dependent channels spread out here, I get voltage-dependent channels spread out here. So I'm going to have voltage-dependent sodium channels and potassium channels here. I'm going to have voltage-dependent potassium channels and sodium channels here, same here and same here. So what can happen now is if sodium comes in here, it can go down the axon and stimulate the next channel. And then sodium will come in here, because that channel the voltage was raised, and it'll come over to this one. So now that sodium is going to make this channel say, hey, I'm not at minus 70 anymore, I'm at minus 55, so I'm going to open and let sodium come in. And you can see that you can step down the axon that way. So the key here is to get these first guys to open. So that's why we're keying on the axon hillock right now. So if you can get the axon hillock to minus 55, sodium's going to come in and get down to this one to turn this ion channel on. Then sodium's going to come here and get down to this ion channel and get this ion channel to be turned on. Then the sodium's going to make it to this one, and you've got a signal that's going to propagate down a neuron. So if your brain has decided to wiggle your big toe, it can send the signal down to the end. And we're going to see in a little bit that the point is to get the end, the synapse here, to plus 30, because then that will initiate a signal from this neuron to whatever its target is. Okay, so long divergence there, but the point I was trying to get is you've got to get the axon hillock, these sodium channels in the axon hillock, activated in order to kick off the signal to do something. We're going to just be really metaphorical here, really simplistic, and say maybe you need 1,000 sodiums here to get these sodium channels opened. Well, these different pros out here are going to have various abilities to get 1,000 sodiums down to this axon hillock, and those abilities are defined by Ohm's law. And maybe it's just going to be best if we get started on it, because first of all, the first part of Ohm's law that determines the strength of input is if the synapse is closer to the axon hillock, it's going to be a stronger synapse. So Ella here is really, really strong. If Ella is with me and it's raining, I'm going to take an umbrella. Maybe one of the reasons she's strong is because she's right next to the axon hillock and right next to those sodium channels. Mother-in-law is way out here. So when she says take the umbrella, all the sodium that she's going to put in to get me to 1,000 sodiums down here is way out here. It's got to go a long ways. So Ella is at an advantage. She's going to be stronger because she's closer to the axon hillock. The other thing that determines the strength of the input is the size of the dendrites. Maybe we'll key here on parking. Parking is on a little bit bigger of a dendrite here than mother-in-law. So if both of these, just disregarding how far they are from the axon hillock, but if both of these can put in the same amount of sodium, just the fact that this is a bigger dendrite means this parking is going to be a stronger synapse. Maybe another metaphor is if you're trying to move 1,000 people and you've got nice big halls to move them down, you're going to be able to move them easily. And so switching back to the metaphor, if you can move 1,000 sodium ions down this nice big hallway, mixing my metaphors, then it's going to be easier to get that 1,000 sodiums down here. Now, if you're trying to move 1,000 people through really narrow hallways, they're going to get all spread out. It's going to be hard to keep them as a group. And again, mixing my metaphors, if you put 1,000 sodium in here, in this narrow hallway, by the time they get down to the axon hillock, they're going to be so spread out that they're not going to have that much influence on the axon hillock. The third thing that goes into the strength of the synapse is basically how much neurotransmitter is released, or how much sodium can that synapse put into the target neuron. So maybe Ella, she puts in 20,000, 100,000 sodiums, so you can be darn sure that 1,000 sodiums are going to make it down here to the axon hillock. Maybe mother-in-law, she can only put in 100 sodiums, so she's really, really weak. She's going to maybe play a role if somebody else gets us up to 999. She can weigh in on a decision, but on her own, she's not strong enough to make me get 1,000 sodium ions down here to the axon hillock and trigger the response. The other thing I want to point out about this is learning. As one of the main things is after you make a decision, you want to learn from that decision so that it influences future decisions. And basically all three of these might play a role in learning, but some of them more than others. So first of all, the wider the dendrite, well, let's start with one. The closer the synapses to the axon hillock. There's some evidence, pretty weak evidence, that maybe, let's just talk about mother-in-law. Mother-in-law has an uncanny ability to recognize when it's going to be a real bad rainstorm. And so when mother-in-law, after 25 times my mother-in-law saying it's going to rain and I don't take my umbrella and then it really just downpours, I finally learned my lesson that when mother-in-law says it's going to rain, it's going to be quite a bit of rain, so you might want to take your umbrella. So how did this synapse become stronger? One thing it can do, although there's really weak evidence, is that it can grow a tangent that will move closer to the axon hillock. So it can grow over here, or maybe it can grow another synapse over here and move closer to the axon hillock. There's pretty good evidence that activity will determine the size of the dendrite. So if we start firing this axon, or if we start firing the synapse a whole bunch, the dendrite will respond by getting larger. It's like if you keep forcing 100 people through a hallway or 1,000 people through a narrow hallway, eventually something's going to happen to get that hallway to get bigger. So if you keep putting sodium in here, it will make that dendrite get bigger. So that's another way to learn. But probably the quickest way to learn is just to release more neurotransmitter. Mother-in-law has convinced me that she knows when I should take an umbrella, so this synapse is just going to release more neurotransmitter. So maybe the first 25 times mother-in-law says it's going to rain, I release 100 sodiums. Doesn't have any effect on the axon hillock. Maybe I finally learned my lesson, and now mother-in-law is going to release 100,000, a million sodium ions just by releasing more neurotransmitter. So there's definitely going to be enough sodium that gets down here to get my pretend or metaphorical 1,000 sodiums down at my axon hillock. So just trying to point out how learning can basically occur then. I think that's it for the second run through. We're going to come back through the run through in the third time and talk about synaptic transmission and how you have the negative effects. So this is the third run through of our umbrella metaphor, and I basically want this run through to stand on its own. So I'm going to repeat everything in this run through that I've talked about in the first two run throughs, so that this one will be the complete story that you'll need to study. I want to start by talking about what you do need to study and what's going to be expected of you on the test. And basically, you'll be asked to reproduce this whole drawing on the test. You'll get a blank 11 by 17 sheet of paper, and you'll redraw this in full, and I'll check it against a list of everything that's on this drawing right now. The pedagogical argument here is that if you can put everything together into a story, it's not going to be that hard to reproduce this drawing. It will be awfully difficult to simply memorize this drawing if you don't understand things. Again, the philosophy is to try and present each individual part of this story really, really simply. So this can be viewed as like chapter 1 of a book, chapter 2 of a book, chapter 3 of a book. Hopefully those are fairly simple little parts of the story. And then it's basically on your shoulders to put this all together so that it all makes sense. And then once it makes sense, it's going to be really easy to reproduce it. The main goal here, or what we're mainly trying to understand here, is how nervous tissue makes decisions, or how neurons make decisions. With some pretty basic thoughts, it's really easy to understand how you make decisions, how your decisions involve pros and cons, and those pros and cons can be of various strength. And these decisions can be everything from, like our metaphor today, do I take an umbrella, to is that a T or an I? Is that the word the or them? Is my car moving to the left and so I need to steer a little bit to the right to stay in my lane? Is that something off to the side of the road that I need to respond to? These are all small little decisions that guide our overall consciousness. But if we go back to the neural level, basically what neurons do is they gather a lot of input, pro and con input, and they come to a yes or no decision. Another really critical subtext is we're starting to begin to look at electrolytes, really important electrolytes like sodium, potassium, calcium, and chloride. Now, we kind of touched on this back when we talked about chemistry, and we talked about ion bonds, and we talked about how sodium and chloride will dissociate in water, and they'll kind of relate to each other, and they have a charge reaction and things like that. And so we're going to build on that now, and it's going to be really an important build because sodium, potassium, calcium, and chloride are going to come up continuously throughout AMP1 and AMP2. It's one of the last things we talk about in AMP2 when we talk about the urinary system and electrolyte balance. We're going to talk about when we talk about how muscles contract. We're going to talk about with the endocrine system because calcium has a role there. We're going to talk about with the reproductive system because calcium has a role there. We're going to talk about it and how it sets the heart rate because sodium and potassium set the heart rate. We're going to talk about how muscle contracts in the heart as well. So anyway, these ions, these electrolytes are going to keep popping up over and over again. And one of the biggest things I want you to take away from AMP1 and AMP2 is respect for these electrolytes and this electrolyte balance. One of the hard parts of developing that respect is the body is so good at regulating these ions, and they so rarely get off. But if they do get off, if there's an imbalance in these ions, it's almost always immediately tragic. Some examples that you can think about are Terry Schiavo, due to diet problems, had an imbalance of potassium that shut down her heart and led to a coma. Or another really kind of unfortunately infamous event happened, I think, last February with the water drinking contest. If you drink too much water, it causes water toxicity, which basically is relating to these electrolytes because you're diluting out these electrolytes. And as you'll see here today, that's going to affect how neurons function. So beginning again at the bottom of this sheet with the model cell, this is essentially a model cell. It's got a few things added to it now because we're in our third run through, but at its heart, you have a sodium potassium ATPase and you have a plasma membrane, and you're distributing sodium and potassium due to that sodium potassium ATPase. And again, this model cell will represent any cell in the body, and this certainly is going to represent this soma right here. This is the main thing that we're going to focus on right here, is we can pretend that this sodium potassium ATPase down here is actually in the membrane of this neuron. So let's talk about this sodium potassium ATPase first. First of all, ATPase means it's an enzyme that breaks down ATP. And what it does is it moves sodium and potassium across the plasma membrane. Specifically what it does is it pumps sodium. So a lot of the time, this is called the sodium-potassium pump. And again, specifically what it does is it pumps 3 sodiums out and 2 potassiums into the cell. It's going to set up 2 gradients. The first one hopefully is fairly clear, that if you're pumping sodium out, you're going to end up with more sodium on the outside than on the inside. And if you're pumping potassium in, you're going to end up with more potassium on the inside than on the outside. The other thing might be a little bit harder to see is it's going to set up an electrical gradient too, because you're pumping 3 sodium ions out or 3 positive charges out, and you're only pumping 2 potassium ions in or 2 positive charges in. So essentially what you're doing is you're pumping positive charge outside the cell. Now the first guy that talked about this, he had a choice. He could talk about the outside of the cell is positive relative to the inside, or, same thing, he could say the inside is negative relative to the outside. And he chose to speak about the inside of the cell as being negative relative to the outside. More specifically, it's about minus 70 millivolts. Millivolts, or volts, is the unit of charge. We can also speak of this as the voltage of the membrane, which is abbreviated as Vm. So Vm equals minus 70 millivolts, or MV. So now the sodium potassium ATPase has set up these initial conditions, and hopefully we can see that ions want to move. But let's get more specific about why do ions want to move, and that's number 2 here. Again, it comes down to those 2 gradients set up by the sodium potassium ATPase, the chemical gradient and the electrical gradient. The chemical gradient is simply that sodium is stacked up on the outside of the cell, and it would like to move away from itself. One sodium ion would like to move away from other sodium ions just by diffusion. Potassium has the same situation. It's stacked up on the inside of the cell. Each potassium ion would like to get away from other potassium ions by diffusion, so it wants to move outside the cell. There's also an electrical gradient set up by that minus 70 millivolts inside the cell. And sodium and potassium are going to react differently to that minus 70 millivolts. Because sodium is on the outside, it's positively charged, and it wants to come into that negative charge because opposites attract. So the positive sodium wants to be next to that negative charge. So sodium is going to be drawn into the cell by the electrical gradient. Potassium is already next to that minus 70, so it really doesn't want to leave if you look at just the electrical gradient. Potassium does not want to go against the electrical gradient. Now if you put the chemical gradient and the electrical gradient together, the chemical gradient is going to be much stronger than the electrical gradient, and so potassium is going to leave. Another way we can think about that is if you could open up a channel that would let both sodium and potassium through, what would happen? Now this is a rare situation because most of the time an ion channel is just going to let one type of ion through. So there's a sodium channel that lets sodium through, or there's a potassium channel that just lets potassium through. There is one specific case that is going to come up when we talk about muscle physiology, where a channel will let both sodium and potassium flow through the same opening. And in this case, sodium is going to come in faster than potassium leaves. And that's because sodium again is being drawn in by both the chemical gradient and the electrical gradient, while potassium wants to leave by the chemical gradient, but it wants to stay by the electrical gradient. So hopefully it's clear that ions want to move. The next question then, question number 3, becomes how do those ions move? And the answer is ion channels. And there's 4 main types of ion channels. There's voltage-gated channels that are going to respond to the voltage of the membrane, or VM. There's ligand-gated channels that are going to open when a chemical binds to them. There's mechanogated channels, and they're responding to force. And the main example here is going to be a sound wave. And then there's leak channels that are really, really small, but they're open all the time. So I'm focusing in a little bit more, and I'm going to start on the voltage-gated channels so that we can describe why those open and close. We're going to start with something called a gate, and obviously these are real simple cartoons. And right here is our gate, and that's going to keep the channel closed. On the gate are positive charges in the case of the voltage-gated channel. These positive charges are going to respond to the voltage of the membrane inside the cell. If the inside of the cell is like minus 70 millivolts, those positive charges are going to be attracted to the negativity inside the cell, and so this gate is going to stay slid down. If we change the voltage towards positive, now here I've got it as plus 30 millivolts, but in the case of a sodium channel it might be just a small shift in voltage up to minus 55 millivolts. But if you move a little bit positive, then those positive charges say, I'm not really attracted to the inside of the cell as much now, so I'm going to slide out. And when it slides out, the channel is open and an ion can pass through. Ligand-gated channels are considerably simpler. Basically, a ligand is a chemical that when it binds to the gates, it opens the gates. If there's no chemical bound, the gate stays closed and no ions can pass. Again, mechanogated are going to respond to force, and in the inner ear, you have these types of channels with small little hairs sticking out. And when sound waves come along and push on those hairs, it can open the channel. If there's no sound wave to push on the hair, then the channel stays closed. Leak channels are really, really small channels that just let sodium flow in all the time and potassium flow all the time. To be honest, for the most part, we're really only concerned with voltage-gated and ligand-gated channels at this time. And you're going to see those popping up. You'll see them on this figure here, that voltage-gated channels are drawn here. Ligand-gated channels are drawn over here. So these are going to pop up throughout the umbrella metaphor. Mechanogated and leak channels aren't really in this lecture, but we're going to need to have an understanding of those when we do special senses, so that's why we're covering them here. Our next question is what happens when ions do move, and the answer is that the voltage of the membrane changes. I'll take you down here to the cell model, basically point out that what's going to happen if sodium does come into the cell. Sodium is positively charged, and if it's allowed inside the cell, it's going to bring that positive charge. It's going to make that voltage of the membrane go more positive. A little bit harder to see is if potassium leaves, it's going to take its positive with it. It's going to make the outside of the cell more positive, which means the inside of the cell is going to be more negative. So when potassium leaves, it makes the inside of the cell more negative. So what we have here is the opportunity to change this voltage up to positive voltages and then back down to negative voltages. And this ability to change voltage by letting sodium come in and raise your voltage and letting potassium leave to bring your voltage back down is the basis of cellular signaling. It's about as fast as a signal as you can create. It's not as fast as electrons, but these ions move pretty fast. And if you want to get some signal from one end of a neuron to another end of a neuron, changing the voltage is a pretty quick way to do it. Before we get into detail about these voltage changes and how you graph it out, I want to just get into a little bit more detail. So focusing back on this model cell, I just wanted to point out some details of the different types of voltage-dependent channels. We have two different types of voltage-dependent channels. I mean, all over the body you have different voltage-dependent channels. You have voltage-dependent calcium, you have different types of voltage-dependent sodium channels, and different types of voltage-dependent potassium channels. And that's going to be important, especially when we get to cardiac function. But right now we're going to talk about two types of channels, a voltage-dependent sodium channel and a voltage-dependent potassium channel. And they're very different as far as when they open. First of all, the voltage-dependent sodium channel is going to open at minus 55 millivolts. So to review, there's this positively charged gate that when the inside of the cell is minus 70 millivolt, this gate is going to be attracted to the inside of the cell and it's going to slide down and be closed. But if we move as little as 15 millivolts up to minus 55 millivolts, this gate is going to slide open and the channel is going to be open to let sodium come in. Kind of a unique feature of the voltage-dependent sodium channel is something called an inactivation plug, and this is going to swing in shortly after the channel is open, basically close all the sodium channels down. The voltage-dependent potassium channel is going to open at plus 30 millivolts, and when it gets to plus 30 millivolts, potassium is going to leave. So hopefully you've started to see the basis here of changing the voltage. Something's going to happen to get us from minus 70 millivolts up to minus 55 millivolts. Sodium channels are going to open, and sodium's going to start coming in. When that sodium comes in, it's going to raise the voltage even further. It's going to raise it all the way up to plus 30 millivolts. At that point, the inactivation plug is going to swing in and close the sodium channels, and the potassium channels are going to open. When the potassium channels are open, potassium is going to leave and bring our voltage back down to negative. So you have the mechanism here. Open up the sodium channel, get my voltage up to positive values, close that sodium channel, now open up the potassium channel and get my voltage back down. Now we can formalize these voltage changes by graphing them. What we're going to do is we're going to graph membrane potential here, and some of the key membrane voltages are minus 70, minus 55, and plus 30. We're going to graph the changes in these voltages over time. And what we get is a figure that is called an action potential. Basically, we're going to start right here at rest, and this would be the situation when there's no rain right now. My umbrella neuron is not doing anything right now, it's at rest. Now if something happens, you hear some raindrops on the roof or something like that, something, and we're going to leave it as something right now, but we're going to clarify it in a little bit. Something's going to get my voltage-dependent sodium channels up to minus 55. Now when they open, they're all going to open, and they're going to bring the voltage up to plus 30. So that's why I have this figure here. The sodium channel is open and the potassium channel is closed, and this state is called depolarization. When we get to the top here, the inactivation plug is going to swing in. Hopefully you can see that right there. And the sodium channels are going to close. The potassium channels are going to open. And this is going to do something called repolarization, which means it's going to take our voltage back down negative. The potassium channels stay open a little too long, and that causes an undershoot, or it's also called a hyperpolarization. The sodium-potassium ATPase gets everything back in order. So it gets the sodium back out, potassium back in, and that brings our voltage back to minus 70. Something else to mention, though, are refractory periods. There's refractory periods in the action potential, and one is called an absolute refractory period, and one is called a relative refractory period. What refractory period means is it's hard to get another action potential. And that can be absolutely hard to get another action potential. And that's what the absolute refractory period is. You cannot get another action potential if you're already starting up on an action potential. And basically what this comes down to is there's no super duper action potentials. There's one size of action potential no matter where you go in the body. You don't get big action potentials and small action potentials. The way you actually code for something that's a simple touch or a really hard touch or something that's really painful, basically the way you code for intensity is how fast the action potentials come, not how big they are. Now again, the reason that there is no super duper action potential is because once the sodium channels open, they all open. There's none that lay in wait in case there's a bigger signal. They're all open. And so if they're all open, you can't open any more than all of them, and so you're always going to have the same signal. So once you've started up on an action potential, all the sodium channels are open, so you can't get a bigger action potential, or you can't get another action potential in the middle of an action potential that's already occurring. Now once those sodium channels start to close and the potassium channels start to open, technically you can get another action potential, but it's really, really hard. That's why it's still called a refractory period. And the reason it's hard is mainly because those potassium channels are open. If we go down here to the model cell and we think about, well, to get our voltage back up, we have to have sodium coming in. But if the potassium channels are open and potassium is leaving, then it's a bit like trying to fill up the bathtub when the drain is open. You can do it, but you have to make sure that the water is coming into the tub faster than the water is leaving. So in this case, back to the cell, the sodium has to really, really be coming in. It has to be coming in faster than normal because now it has to offset the fact that the potassium is leaving. So you can get another action potential once you've started down, but it has to be a super strong signal. And these are reserved for cases when you really, really need a lot of action potentials in a row. And if we go back to talking about how you code for intensity by the frequency of the action potentials, this means it's really hard to stack up the action potentials really, really close to give a really, really intense signal. But if you do, now you do have that super duper signal, because not only have you stacked the action potentials close, but you've stacked them so close that more sodium is coming in than potassium is leaving. So you got that extra turn the dial up to 11 signal when you actually have such an intensity that the action potentials are right up next to each other and impeding on that relative refractory period. Now let's go down here to this lower left where I'm going to describe the two types of potentials. And this is where you really begin to understand what an action potential is. What an action potential is it's a potential that can move. And that's set up by the fact that you spread out voltage-dependent channels. And in this little cartoon, I've got a voltage-dependent sodium channel with sodium coming in. And if sodium comes in through that channel, it's going to spread to the next channel. And now that channel and the gate in that channel is going to say, I'm at a more positive voltage on the inside, so the gate's going to open, and now this channel is going to start letting sodium come in. Sodium's going to migrate over to this channel. This gate is going to sense that positive sodium on the inside, say the membrane voltage is not minus 70 anymore, it's minus 55, so now that one's going to open. And you get this jumping from voltage-dependent channel to voltage-dependent channel, and that's really what an action potential is. And where that occurs in a neuron is right along the axon. So you have myelin in here, you have gaps in the myelin that are called nodes of Ranvier, and in those nodes of Ranvier there's voltage-dependent sodium and potassium channels. So again, if sodium can come in here, this area is called the axon hillock. If sodium comes in here, it spreads, and it spreads to the next node of Ranvier where there's a voltage-dependent sodium channel waiting. Sodium comes in, and it spreads to the next node of Ranvier where there's a voltage-dependent sodium channel waiting. That sodium channel says it's not minus 70 anymore, it's minus 55, so I'm going to open and I'm going to let sodium come in. That sodium technically spreads in both directions, but the important direction is in this direction, because now this sodium channel is going to sense that voltage change and it's going to open. I'm also going to bring back that inactivation plug, which we can look at in the cell model. Basically, that inactivation not only closes the sodium channel, but it keeps it closed, and it makes sure that the action potential travels in only one direction. So bringing in two things there, don't mean to be confusing. Bringing in the action potential, which means things will jump down the axon in what's called saltatory conduction. And also, the reason we have that inactivation plug is it prevents the action potential from backing up the axon, basically going upstream. Because even though the sodium might flow back to the previous node of Ranvier, the sodium channels in that node of Ranvier are going to be inactivated. And again, this keeps the action potential going in one direction. The other type of potential is just a graded potential. In a graded potential, there aren't voltage-dependent channels to help propagate the signal. So when the sodium comes in, it just spreads around. Graded potentials occur out here. So at this point, we've kind of hit on the fact that this axon hillock is really important, because this is where there's a huge cluster of voltage-dependent sodium channels that are trying to get to minus 55 millivolts. And really, the whole decision about whether I take an umbrella or not is made right here at the axon hillock. What it's going to do is weigh pros and cons. So it's going to weigh information from pro neurons out here, pro synapses, and negative synapses, and decide, do I fire this axon? How it decides that is basically, do I get enough sodium to get up to minus 55 millivolts to open these sodium channels? Because if they do get opened, then sodium's going to flow in. You're going to send your signal down the axon, and you're going to signal to another cell. This umbrella thing is a go, so start planning it or squeeze the muscles in the hand to pick it up. But we are going to take an umbrella. Things like that. So then the question becomes, how much sodium does it take to get these sodium channels open? And we're going to just put a fake number on it. We're just going to say 1,000 sodium ions. Now it's going to be way higher than that, but keeping it simple, like something like 1,000, is going to help us focus on what's going to make us get to 1,000, like Ella, and what's going to keep us from getting to 1,000, like I want to look tough. But for this first part, we're just going to talk about the pros. What are the things that are going to try and stimulate the axon hillock? Because there's 3 things that go into how strong Ella's effect is on the axon hillock, how strong the mother-in-law's effect is on the axon hillock, how strong my hair is looking fine today is on the axon hillock. And these strengths of input are defined by something called Ohm's law. Now, Ohm's law is usually described in terms of electricity. It's like how fast current flows is dependent on how much it's pushed by the voltage over how much resistance there is. But Ohm's law will describe a lot of things. It describes water through a hose too. How fast the water comes out of a hose depends on how much pressure is on the hose behind it and what resistances are on that water. So if you have a big hose, you have less resistance and more water is going to flow. Things like that. Ohm's law also describes the likelihood that Ella is going to get 1,000 sodiums down here to the axon hillock. It's going to describe the probability that mother-in-law is going to get 1,000 sodiums down to this axon hillock. The first thing that's going to describe whether a synapse has the intensity or the strength to stimulate the axon hillock is how close is it to the axon hillock. So I kind of imagine in my brain the Ella synapse is really, really strong, and one of the ways it can be really, really strong is it's right next to the axon hillock. So if it dumps 1,500 sodium ions in, chances are 1,000 of them are going to make it to the axon hillock just because that synapse is so close to the axon hillock. Mother-in-law, on the other hand, whatever sodium she dumps in here, it could go in a variety of different directions. It's going to get spread out by the time it gets to the axon hillock. So the fact that this synapse is so far from the axon hillock is one of the reasons this synapse is relatively weak. Another thing described by Ohm's law is the width of the dendrite. And basically a metaphor here is if you wanted to move a bunch of people, would you want wide hallways or would you want narrow hallways? With wide hallways, you could move those people and you could keep them right together. If you have narrow hallways, they're going to get spread out. So to kick off the axon hillock, we need 1,000 sodiums in a clump to get down here. So if we've got a nice wide dendrite, or in this case on this parking dendrite, a nice wide dendrite, it's going to be easy to move the sodium in a clump down to the axon hillock and make sure we get 1,000 sodiums down here to stimulate the axon hillock. If you're way out here on mother-in-law, really, no matter how much sodium you dump in there, it's going to get spread out. And so it means this synapse is going to be very, very weak. It's going to be hard for the synapse to get 1,000 sodiums down here. The third thing is simply how much neurotransmitter is released. So when I took her that first time, and it was a bad situation, I needed to learn once. I needed to learn really quickly. And probably the easiest way for a neuron to improve its performance is to release more neurotransmitter so more sodium is released into the target neuron. So if Ella releases 500,000 sodium, it's pretty likely that 1,000 sodium are going to stimulate the axon hillock. And kind of extending on that, let's say for example, let's extend into learning. Let's say for example that mother-in-law has this uncanny ability to predict really, really strong thunderstorms. And so for the first 25 times my mother-in-law says, DJ, it's going to rain today, you should take an umbrella. I blow her off and I get really, really soaked in a downpour. Eventually I'm going to want to learn. I'm going to want to learn to make this synapse stronger. It's very weak right now because it's so far away. It's on a very narrow dendrite and it's not releasing a lot of neurotransmitter. So how is it going to become stronger? Each of these methods can lead to improvement, but some are going to be easier than others. For example, a really weak one, but it might actually occur, is this synapse might grow an additional synapse off to the side that's going to be closer to the axon hillock. And that does happen sometimes. Those are called collaterals. There is research that if a synapse is used often, the dendrite will get wider. And so if this synapse is releasing a lot of neurotransmitter, releasing a lot of sodium into here, the dendrite will actually grow, and that will improve this synapse's performance. Again, a nice wide dendrite means that the sodium can move in a clump and make it down to the axon hillock. But probably the most likely, and I already alluded to it, the most likely way that you're going to learn is you're going to have the synapse release more neurotransmitter. So mother-in-law, if she releases 1,000,000 sodiums, it's likely that 1,000 sodiums are going to get down here to activate the axon. So that's a look at how you can get different strengths of input, but it's also important to keep in mind that all these things kind of add together. So all the pros will add together to get 1,000. So maybe Ella's not with me. That's not going to get me my 1,000. But maybe parking plus mother-in-law plus the hair looks fine. Those three together are going to put in enough sodium that I get to 1,000 sodiums at the axon hillock. So just to come back to it and say it for about the 25th time, is neurons make decisions. Decisions involve pros and cons, and those pros and cons can be of various strength. And we've kind of already covered now how you can get pros and how they can be of various strengths, but we haven't talked about cons. And so to talk about cons, how do you negatively influence taking an umbrella? How does I'm tough shut this I'm taking an umbrella neuron down? First of all, I'm going to go over to the model cell and point out that I've added another ion, the chloride ion. Now, I didn't put the chloride ion in the first and the second versions just because we didn't need it up to then and I didn't want to add the clutter, but we definitely need it now, so now it is in the third version of the umbrella metaphor. Please notice that chloride is negatively charged and it's more concentrated on the outside of the cell. So one of the ways you can negatively influence the axon hillock, prevent it from getting to minus 55, is make the cell more negative. We can see that in a couple places. If you have to get to minus 55 and you're at minus 80, it's going to be harder to get up to minus 55. How do I get to minus 80? The simplest way is to let these negative chlorides in. If a negative chloride comes in, it's going to make you more negative. You could also open up a potassium channel, and when the potassium leaves by diffusion, it's also going to make the cell more negative. So everything up here under cons were in red. Notice that a con neuron is going to either let chloride in the umbrella neuron or it's going to let potassium out. Now these things, because it's changing the potential, are called inhibitory postsynaptic potentials. So the postsynaptic neuron, here's the presynaptic neuron, is the red neurons coming in or the green neurons coming in, and the umbrella neuron is what's called the postsynaptic neuron. So that's where the inhibitory postsynaptic potential comes from. Again, presynaptic neuron and postsynaptic neuron. While changing the membrane voltage to more negative voltages is probably the easiest to understand way that an IPSP has its function, there is another way that it works, and it's called a shunt. Basically what happens is these channels can just simply sit open. Then every time a sodium comes in, these channels will allow a potassium to leave or allow a chloride to leave. So then what's happening is every time a sodium comes in, it wants to bring in its positive charge, but it's offset by the negative charge of a chloride coming into, or offset by the negative charge of a potassium leaving. So it's kind of having a negative effect. Just like back to the bathtub metaphor, you can inhibit filling the bathtub by opening the drain. In this case, sodium would be pouring into the bathtub, mixing metaphors, but potassium and sodium would be leaving through the drain, and it would offset each other. So this is a technical, kind of a little bit hyper-technical way that these actually probably inhibit. On the pro side, it's much more simpler, because really the only way to change this voltage more positive is to let more sodium come in. And now that's called an excitatory postsynaptic potential, because it's going to excite the postsynaptic cell. In our case, it's this yellow, do I take an umbrella today, neuron. So then here, now that we've finished up with cons, take a moment to think about how there's kind of a quasi-math that's occurring in the postsynaptic neuron. Sodium's coming in from some pro over here, more sodium is coming in from this pro over here, negative chloride is coming in from this con over here. So this mash of sodium coming in, chloride coming in, potassium leaving, that does a certain amount of mix-up math to determine, do you get those 1,000 sodiums down to the axon hillock? So this is why when we make decisions, we weigh a lot of pros and cons. The umbrella neuron is weighing a lot of IPSPs and EPSPs to determine, do you have enough sodium coming in to stimulate the voltage-dependent sodium channels in the axon hillock. If you do, then it's a yes decision, and if you don't, then it's a no. The next thing to talk about then is synaptic transmission. So if you've got these chloride channels opening, these potassium channels opening in the postsynaptic neuron, or these sodium channels opening up in the postsynaptic neuron, how did that signal get to them to open up? And it's really a fairly simple process we're going to outline here. Basically, on your drawing in class, you can either draw the figures or you can write it out. It all begins at getting to plus 30. You'll notice down here I've got plus 30, that's a key number. So when this action potential goes down, we make the presynaptic neuron plus 30. When the presynaptic neuron gets to plus 30, now there's a voltage-dependent calcium channel. So it's almost the same as the potassium channel and the sodium channel as far as it's got a small little gate that slides out when the channel gets to plus 30, and calcium can come in. When calcium comes in, it opens up neurotransmitter vesicles. You notice these small little circles are filled with black dots. Those black dots represent neurotransmitter, and the little circles represent something called synaptic vesicles. When calcium binds to the synaptic vesicles, they open up. Normally they're pinched closed, and they can just open a small little bit, and they're going to release their neurotransmitter, and they're going to bind to ligand-gated channels, the same kind of channel we talked about over here, ligand-gated channels. When the neurotransmitter binds to those ligand-gated channels, they open up, and in this case they let sodium in. Over here in the case of the cons and the IPSPs, they let chloride come in or potassium leave. Now there's one more critical thing, and there's kind of a rule of neurotransmitter release, which is you should release enough neurotransmitter to stimulate every postsynaptic receptor once and only once. So every receptor gets one neurotransmitter molecule, and then you have to get rid of the rest while those stimulated receptors are doing what they do. There's 3 ways that you get rid of the rest. And it's important to understand these processes because we have pharmacological interventions. We can give drugs that affect these processes. So just a little bit more closer of a look. The first process I'll talk about is something called reuptake. And so after we release all that extra neurotransmitter, one way we can get rid of it is to take it back up into the presynaptic terminal, and that's called reuptake. And one of the reasons this is important is because this is what SSRIs, selective serotonin reuptake inhibitors, or antidepressants do. They inhibit this process, and they leave the serotonin in the cleft longer, constantly stimulating the postsynaptic receptors. Is this effect of the drug takes place almost immediately, within hours of taking the drug. But maybe most of you know that antidepressants generally don't start working for 2-3 weeks at a minimum after taking the drug. So it's clearly not leaving the serotonin in the cleft that has the antidepressant effect. It's thought that that serotonin left there causes the body to say to these serotonin receptors, I'm being stimulated too much, so I'm going to take some of those away. And it's the taking away of those serotonin receptors that has the antidepressant effect, and that process is what takes 2 to 3 weeks. Another mechanism in different synapses is enzymatic breakdown. So I've got this small little circle which is supposed to represent an enzyme, and it can grab onto any neurotransmitter that hasn't found a receptor and basically break it down. This is going to occur mainly in the synapse between a motor neuron and a muscle. And sometimes there's a disorder called myasthenia gravis, where that receptor that's supposed to pick up the neurotransmitter gets eaten away at by the body's own immune system. And one way you can give a drug to fight that is to inhibit the enzyme. If you inhibit the enzyme, the neurotransmitter sticks around longer. So even though there's less receptor, the muscle still gets stimulated, and you don't get paralyzed as fast, or the muscle weakness is attenuated a little bit. The third mechanism of getting rid of excess neurotransmitter is some of it just diffuses out of the synaptic cleft area. The last thing to talk about are what are the different types of neurotransmitters, and this is an oversimplification to be sure. But in general, we can divide neurotransmitters up into direct type neurotransmitters, and these are going to be the type that bind to ligand channels and open up those channels. You can also have indirect ion channels, and these are going to bind to G proteins, something we touched on early in this class. Basically what a G protein does is it binds something to the outside, and then through a cascade effect, it multiplies that signal up millions and millions of times, so you can change a whole host of proteins or a whole host of processes inside the cell. Direct ion channel receptors are things like amino acid. It's like GABA and glycine, which tend to have inhibitory effects, which means they are going to bind to which type of channels. They're going to either let chloride come in or let potassium leave. There's also NMDA and glutamates. These are going to have EPSB effects or stimulatory effects, so they're going to open sodium channels. There's acetylcholine as a major type of neurotransmitter, and just to make it more confusing, there's 2 different types of receptors, and one of them is a direct ion channel type neurotransmitter, and the other one responds indirectly through G proteins. Nicotinic acetylcholine receptor is the receptor that receives the neurotransmitter from a motor neuron and stimulates muscle. Muscarinic, again, works through G proteins, and this is a major receptor in the parasympathetic nervous system. You have neurotransmitter called biogenic amines, which are further divided into catecholamines like norepinephrine, epinephrine, and dopamine. And then you have indolamines like serotonin and histamine, which are related to things like mood. There's different peptides, so really small proteins. There's one that's called substance P that tends to increase pain, so if you injure something, you actually want more pain to that area sometimes. You want it to be hypersensitive so you don't use that region. Or it's also responsible for after you cut yourself and it swells and the area around the wound becomes more painful. That's something substance P is thought to do. Endorphins have the opposite effect, so you get like a runner's high, or endorphins are thought to be given off in cases of extreme pain, and they reduce pain. And then there's novel neurotransmitters like carbon monoxide, nitrous oxide, and ATP. So that's the neurotransmitters. So that's the umbrella metaphor, and basically I'm hoping that if you look at each individual chapter in this metaphor, they're fairly simple. The difficulty is putting them all together and making it make sense as to how neurons make decisions. And the first step of that is just how it makes sense in terms of the umbrella metaphor. And the next step is, can you apply it to basically other decisions that your brain makes? Whether it's a line that's vertical or horizontal, whether it's this word or that word. How do you apply these decisions to keep your car moving straight down the road? Or even more complex decisions about, do I go out to dinner tonight or do I go to class? On the test, I definitely would like you to come up with your own decision-making process. Don't just copy, do I take an umbrella today, and try and be a little bit more creative than, do I take a coat today? A common one is, do I go to class today? Again, you should be able to extend this metaphor up into higher order conscious decisions like, what are my political affiliations? What are my goals in life? How do I choose my friends? To simple cognitive processes like reading and turning left and following directions and things like that. Or, how do I feel right now? Do I feel like an idiot and I need to listen to this darn thing again? Or do I feel brilliant? Which is what I'm hoping for. Because you see that at the very base level of consciousness, neurons make decisions, and the processes are pretty simple, although they add up to pretty complex behavior. Or maybe you just go take a nap.